Hello everyone, welcome to this tutorial class of X-ray crystallography course. I hope all of you are following the lectures on the phase diagrams and grain size calculations and so on. And you also must have studied about the Scherer formula, how it is useful in calculating the grain size and so on based on the line broadening of X-ray peaks. So, if you look at the line broadening effect of X-ray diffraction, one can attribute this to several factors. I hope you have got some idea about this during this course. But one of the reason is about the grain size, right. So, the whole Scherer formula is based upon the line broadening of the X-ray diffraction peak. I would like to solve a couple of problems in that today, and also I will just do some work out some problem on the blackboard using the diffraction, how to calculate the phase diagram, where it is applied, something like, for example, how to find out the solver's line of an alloy and so on. So what I will do is, I will first take up a simple problem on the grain size, just to get familiarization. You all must have studied about this grain size calculations using the ASTM standards, and then it is very elementarily taught how to calculate the grain size using the ASTM reference chart and so on. So, first we will take up some simple problem, then we will move on to the Scherer formula and so on. So, the question is, the microstructure of a polished and etched iron sample under a light microscope shows a nearly uniform grain size. If the ASTM grain size number is 4, determine the approximate number of grains per square mm of the sample. So, this is done by simply this formula. So, where n is the small n is the ASTM grain size number, then you simply use this and then it will be of 8 grains per square mm. So, this is very rough method, but it is very fast method. If you looking for an accuracy, then it is not an advisory to use this method. Generally, researchers use a Scherer equation. I hope you have seen the formula, Scherer formula derivation. We will also post that the lecture of derivation of Scherer formula, and we will now take up one problem using the Scherer formula. So, the question is, a powder sample of nickel contains crystallites having an average diameter of 500 angstrom. An X-ray powder photograph of the sample was taken using copper K alpha with a lambda 1.542 angstrom. Calculate the breadth of the diffraction line corresponding to the Bragg angle 60 degree, assuming that the entire broadening is due to particle size alone. So, here is the assumption: the broadening is due to several factors, but if you assume that this broadening is purely because of the particle size alone, then the Scherer formula is valid. So, how to proceed with that? So, you have the formula, Scherer formulas of this kind. So, you just simply substitute this into this equation 0.9 into 1.542 divided by 500 into cos 60. So, this is B. Simply you can rewrite this equation and then you are going to get something like that 5.55 into 10 to the power minus 3 radian. So, this is the breadth of this X-ray diffraction peak. So, you should also realize that this for much more accurate calculations there is something called Williamson-Hall plots are also being used. We will post that problems and the derivation of that, and then you can look at those problems also in another tutorial. So, where you will be able to appreciate the contribution of the stress, I mean strain and particle size and so on. We have demonstrated where how to separate these effects using the contribution of each, for example strain and particle size on the X-ray line broadening. So, you can use that Williamson-Hall plot method also to find out accurately about the contribution of strain and particle size and so on. So, now what will I do is I will just do one more problem on application of the X-ray diffraction techniques on the phase diagrams. Simple problem. Okay. So, the problem is bit long to read, but so a phase diagram for a hypothetical two component system AB shows a terminal solid solution alpha, that is solid solution of B in A. So, you produce, there are 6 alloys containing 10%, 15%, 20, 30, 35 and 40% of B in A were prepared and they were heat treated to temperatures at 300, 400 and 500 degrees centigrade at temperatures, and it is assumed that high temperature phase is retained by this process. And XRD measurements reveals for the 6 alloys the lattice parameters are 3.524, 3.544, 3.550, 3.57, 3.57 and 3.57 and so on for 300 degrees centigrade, and then 3.524, 3.544, 3.575, 3.585, 585, 585 angstroms for 400 degrees centigrade, and 3.524, 3.544, 3.575, 3.630, 0.630, 3.630 angstrom for 500 degrees respectively. So, using this data determine the Solvus curve of the alloy system using parametric method. So, it is basically the application of X-ray diffraction in determining the phase diagrams. So, what you have seen in the lecture notes, how the parametric method is useful, that has been explained. So, we will now try to use that method again to identify the Solvus curve for the alloy. So, how do we proceed? So, if you plot the alloy content versus lattice parameter you obtained from the X-ray diffraction, we will get the plot for the different temperatures. So, what is that we are going to do? It is basically lattice parameter versus alloy content. So, this is so what we have done is, if you actually use this data and you put it in an Excel plot, it will appear something like this. So, I have drawn it as a schematic, but then if you actually plot these values, you will get a nice straight line kind of. It may not be a straight line, but at least a linear segment you will see. But what you have to appreciate from this plot is, see, after a particular composition, irrespective of the temperature, the lattice parameters become constant. So, see, as the temperature increases, there is a variation in the lattice parameter, but then at this particular composition, after this lattice parameter becomes constant. So, that is something we can use this point, then we can replot this . So, if you look at the intersection where this lattice parameter begin to remain constant, and then if you plot temperature versus percentage of composition, you will get the solver's line of the alloy in the phase diagram. So, that is something you can readily appreciate how this lattice parameter constants are, I mean the X-ray measurements of the lattice parameters are useful to find out the solver's line of the alloy. So, the other problems involving the grain size calculation, as I mentioned, using Williamson plots and so on, you can see it in the another video. Thank you.